Incidentally,
Hmm.
this pore water correction uh, is uh, is not being followed in US. I refer to Bowles,
Hmm.
then one Chinese American Jai Han. So
Okay.
they are not showing this pore water correction anywhere. But in our code it exists. But they are specifically written for silt and fine sand, not for clay. The problem here in the assignment was relating to clay.
Uh-huh.
So,
For clay,
so
I don't think the pore water pressure is required. Okay, let
no, no,
them give the
it is not there.
solution.
Yeah, yeah.
Then we'll discuss on that. And
So whatever answer they are showing correct, that comes only when you apply that pore water correction, which is
well,
not
well,
applicable in the case of clay.
yeah, yeah. Okay. Can you see my screen?
Yes, please.
Okay. It's not coming here. Can you see the slide? Well, I can't see in this.
Yes,
Yes, sir.
You
yes,
can.
yes.
Okay, okay. I'm not sure why I can't see it here.
It is very clear.
Okay. No, in my iPad it's not coming. I'm not sure why. Okay, okay, let's start then. Welcome all. Today is the week 4 discussion session, and we'll be discussing about the some course called Subsurface Exploration Importance and Techniques Involved. I am Balram Shah, the PMRF TA of this course. I am doing my PhD at ISCVAR department at ISC Bangalore. So we'll be discussing about the week 4 lectures that has been uploaded in the CE69 session. Okay, so let's start. So we'll be doing some questions. The first question is, which of the following is not true for geophysical testing methods? Okay, before going to the geophysical testing methods, what all we have completed? Okay, let me see if I can share this. Okay, so before moving on to the geophysical testing, what all we have completed? We have learned how what are the subsurface exploration, why should we do subsurface exploration, and what all we have done to do the subsurface exploration, the trial pits or trenches and all, or the drilling and boring, that is the geotechnical tests. Several geotechnical tests we have done. In that we have done the semi-detect methods like vein shear, then SPT test, then cone penetration test, and halitometer test, pressure meter test, and all. Correct. But in these geotechnical tests, as we have seen, there are advantages and limitations for each of the tests. So what all main disadvantages or limitations you can see say for all these geotechnical tests?
We have a sample.
Yeah. So firstly, what is the limitations for these tests are? Firstly, it's those are the point tests method or point based methods. Point based methods, in the sense, what I want to say is, point based method means the soil type at particular location or the particular depth we get to know in the geotechnical test, the semi direct test or whatever test we have done till now. In that, the soil type at any particular depth or any particular location only we come to know using those tests. Okay, so for limited location and depth. Okay, next, uh, in the geotechnical test, whatever semi-direct test we have seen, what we have seen, it is only applicable till some deep uh, depth, right? Or let us say if gravels or higher than that, something boulders and all are coming, we have to stop those tests there only. So we go for the deeper investigation, but up to a depth only. Correct. So as we do it for like limited locations and all, so what happens, uh, we have to drill, then we have to do the tests and all, so it's kind of time consuming. It will take time for each of the test. Other than that, what is the main caveat? Let us say for large areas with more number of investigation points, more time will be required. As I said, it will be time consuming. Okay, like if there are much bigger areas and we have to do several number of boreholes or several number of testing we have to do, and in that case it will take more time and much cost will also be there. Okay, for the whole area. Now what happened, we divide the in those tests, what we do, we divide the whole area into, let us say the sorry let us say this is the whole area we are doing the exploration. So what we do, we divide it into the into number of grids. Okay, we divide it in number of grids. So with each grid, let us say in for geotechnical test, if we go in that, we have to do at least one or more test for each of the, let us say we have to do one geotechnical test in the first grid, so at least one or more tests should be done in each of the grids for the whole area. Okay, now so based on this number of test, how will consider, it will be based on, it will vary, like if there are different structures, different kind of structure, then different field investigation is required. Let us say some different seismic areas and zones are there. Based on that, the number of tests and all will be considered. So all these things are there. Whole area is divided into a number of grids with at least one or more tests at each location, at each grids. Okay, so for this we have to go for the geophysical testing. Okay, so for this we have to go to the geophysical testing. So these geophysical tests are also called indirect test or non-destructive test. see this sorry, the non-destructive test you might have heard before. Non-destructive tests. So while studying the concrete technology or that part, you might have heard about the non-destructive test. Can you name one or two of those? Anyone?
Ultrasonic pulse, core
Huh.
testing,
Yeah, yeah.
then we have
Ultrasonic
rebound hammer,
rebound hammer test, ultrasonic pulse wave velocity tests, and all.
then load testing also we do
Yeah,
for
correct.
structures.
Several other are there. Rebound hammer, then ultrasonic pulse velocity tests and all. Yeah, so in this here also for the geotechnical thing we do the geophysical test, and these tests are, as I said, these are non-destructive tests. This means what? These are in the first method or the geotechnical method or whatever method we have studied till now. So in that, as it was destructive kind of tests, so it will take more time, right? So as this geotechnical tests are non-destructive tests, it will lead to less time. So less time is consumed in the geophysical tests. Okay, and in the geotechnical test, what we do in the geotechnical test, whatever test we have discussed at a limited location, and hence what we do, let us say we know for the 3 or 4 locations. So what we consider that whatever layer or whatever soil properties are there in between those 2 locations, that are homogeneous, right? Anyway we are considering homogeneous. In this case also we will consider the layers are homogeneous. But what we do for understanding the soil type or properties at any location in between those 2 locations, what we do, simple interpolation, right? So in this, what we do, the interpolation between the 2 locations is not that required, because in those case what we are doing, we are considering the interpolation between 2 locations generally considered to be the same or the linear, okay, over the larger lengths with continuous and 2D methods. So in those, what we go for the, in this we don't have to do for other tests. For other tests we are going for interpolation method, and in that what we do, we understand the how the lithology is changing in terms of depth, or the physical this properties along the survey line, how it is changing. Okay, so in this we don't go for that much of interpolation, because we can easily do it for several number of locations. So hence what we do, hence it measures the physical properties of the medium for subsurface characterization and identification. Okay, so the main advantage you can say for this. So, and firstly, what I said, these geophysical tests are indirect test. Why it is called indirect test? Why this?
Because we are measuring properties indirectly, we measure something else, and from that we try to draw conclusions.
Why geo?
We measure some properties which are related to the target property.
Yeah, correct. So what, as he said, so we consider this geophysical methods as indirect method, because we are not getting any kind of soil sample from it, right? In earlier test what we have seen, we have to take the soil sample, or in some cases we will do the boring, drilling and all, then we'll understand the soil properties. But here what we do, we are not getting any kind of soil sample from any depth, or let us say no sensors are required, or no sensors are lowered into those bores and all. So for that case, so in this test sensors are located only at the surface, and using that we understand the soil characteristics, the properties, or what type of soil is there. Okay, so These are some of the why we are going for geophysical test. Now where all this where these geophysical testings are applicable or where it is useful, these are useful for, let us say, number one, seismic microzonation studies. What does this microzonation study means? Let us say most of the time what we do whenever we are interested to find out what is the material force, sorry, what is the inertial force. So what is the inertial force because of the seismic activity in any particular region nowadays? People are going for, let us say, people are going for more and more regional studies. Okay, we want to do some project at some regional level. Okay, so what we do, we are going for more and more regional studies or the site specific studies, if you say, or sometimes we go for building specific studies also. So in order to find out what is the seismic activity or what is the potential seismic hazard or what is the potential level of ground motion which is expected at that site of interest, like if we are going for building specific studies or we are going for much regional studies, so we have to understand that what is the seismic activity there, or in past if there is any seismic activity, or if there is any seismic activity, what is the potential level of ground motion, what is the potential seismic hazard which is expected at my site of interest. So what we do further, those ground motions will be altered because of the presence of local soil, right? If local soil is there and ground motion is happening, so it will alter the specifications of those soil. So in order to take into account the variation in the local soil properties at whatever site of interest is there over which, let us say, the building is located, so nowadays people are practicing so that one can quantify the subsoil properties. So once the subsoil properties are known, we'll be able to identify or how these subsoil properties are dominating in controlling the seismic variations into the building, right? So for that we go for seismic microzonation studies. Microzonation studies, as I said, we are going for some regional studies or site specific studies, for some cases building specific studies. So we are doing the zone as we are practicing, or we are going for the study which is very micro level. Okay, we are going for the microzonation studies and we are understanding the ground motion, the seismic activities and all. So it is very useful for seismic microzonation studies. Next is the quality control assessment. So in quality control assessment, how it is useful? Let us say the designer has suggested some minimum density of the medium, okay, at the site of interest, whatever site of interest we are having. The designer have given their designs and they have said, or they have suggested that there is this minimum density is there at your site of interest for the medium. Even whenever we are going to subgrade laying or we are going to any kind of filled up areas, so once the site is filled up, we can actually go for the some kind of quality checks. Okay, let us say the area is filled up. Okay, then we can go for use this geophysical testing to do the quality checking. Okay, we can do some test and based on that it will be able to we'll be able to determine what is the strength properties, then what are the densities of the medium. Then we can let us say the designer has given the minimum density and we are getting some density, so in that we can match whether the densities are matching or not. So what are the densities of the medium, so that we can match those densities which are getting from the geophysical test or the geotechnical test with the density provided by the designer. Okay, then comes the forensic investigations of some failed geotechnical structures. Okay, let us say some structures is there which are kind of failure happened. Let us say some abutments of bridges or flyovers or retaining structures, let us say. So in this geotechnical investigation, if the failed structure is there and we are going for geotechnical investigation, what will happen? We are going for some destructive testing. What will happen?
Not desirable. It will disturb the function.
Yeah, it will disturb the function. It will again trigger the distress that is there in the failed structure. uh, it has failed at some limit. Now we are going for more destructive testing. It will increase the distress in the structure. So from geophysical methods, whether there are some problem during the laying of the subgrade, filling for the preparation of abutment, like where we have done the mistake or where was the mistake, we can understand whether there is some approach road or any preparation for the zone of influence for any bridge and all, we can understand from the geophysical testing. Okay, other than that, then we have the validation of the findings from the geotechnical test. Let us say we have the data from geotechnical test, and we can use this geophysical tests and we can validate whether the data or whatever the soil properties or the soil type we have got from the geotechnical test, whether they are correct or not. Okay, findings from geotechnical tests. And it is also suitable for deeper depths. Deeper depth in the sense, let us say geotechnical testing, whatever we have seen, it has some limitations, right? Up to that depth only it can go, up to let us say several kilometers it can go, but yeah, anyway it has some limitations. In these geophysical testing, if we increase the power, then we can go for much higher depth. Okay, so let us move to the questions that we were discussing. So the question was, which of the following is not true for geophysical testing methods? Your options are quick and less time consuming, require trained manpower, less costlier than geotechnical tests, can be done for greater depth. What will be the answer? Oh. Can you see my slide? No, right? Okay, wait. I forgot to share. Okay, now you can see my slide. Maybe. Yeah. Yeah, now you can see. So the question is, which of the following is not true for geophysical testing methods? And your options are quick and less time consuming, require trained manpower, less costlier than geotechnical tests, and can be done for greater depth. Which is not true? First one is the quick and less time consuming. As we said, if we compare from the tests that we have seen before this, like geotechnical test, trial, pits, trenches and all, as we are using some big rigs and borings, drillings and all, it will take much time. But if we come to the geophysical testing, it will be less time consuming. So the first one is correct for the geophysical testing methods. Second one is the required trained manpower. For geophysical testing methods, it's like expensive instrument, and for controlling that we need some skilled people. Okay, so the required trained manpower is required for geophysical testing methods, and hence it is correct for the geophysical testing method. Third is the less costlier than geotechnical tests and can be done for greater depth. For greater depth, anyway, we have seen the geophysical testing methods can be done. So coming to the less costlier for geotechnical tests, even if the instruments that we'll be using for geophysical testing methods will might be expensive, but what is if you consider the whole project, the rigs that we are going, then only not only the rigs that we are using, we have to go for boarding, drilling, the labor cost, and so many other costs are required with the geotechnical test. So if you compare the whole expenditure which is happening in geotechnical test and the whole cost that is you are incurring for the geophysical test, it will be less costlier than geotechnical test. So the correct answer for this will be C. So are you guys with me?
Yeah,
Yes,
but
sir.
all appear to be correct.
Yeah, all appear to be correct, but out of these four, what do you think will be the correct answer? In the why the C is correct, I gave you the explanation. Because if you see the whole cost for the whole project in terms of geophysical testing and geotechnical testing, in geotechnical testing you have to have the machines, you have to have the boarding, drilling, then labor cost and all. And if you compare with one, here what we need, only one instrument we need, maybe it is expensive, but we can have, for if you compare the whole project, then it will come less costlier than that of the geotechnical test, isn't it?
But question is which is not true.
Hmm.
Here all the four options are true.
Yeah, but out of the four, which one do you think is the most apt?
Trained manpower, we can say, because even if you give instruction to somebody,
Hmm.
that ABC can collect that data.
Okay, but how will he interpret those data?
For interpretation, you require a very experienced person.
Okay,
But
so.
for field work, it can be entrusted to laymen also.
Hmm. Okay. Uh, but okay, let's say for trained manpower, the geophysical testing methods, the instruments you have to use, right? So in that, I guess if you in geotechnical test, you have to use the machines, which people will use anyway. B will also be like four. All the four options are true only, but we can go for B and C both. Okay. Here I have given C only. Okay. Okay. Let's move on to the next part. Okay. Before moving on to the next part, okay, I'll share this screen first. Mm, okay. So before moving on to the geophysical testing methods, there are several typical geophysical testing methods which we do. Okay, what are those? Geophysical testing methods. So the testing methods are seismic reflection survey or reflection method, whatever you say. Then seismic refraction survey or seismic refraction method or testing method. Then we have the electrical resistivity method, electrical resistivity survey. Then we have the sounding and profiling methods. Then we have the magnetic anomaly test. Then we have gravity test. or gravity method, if you say suspension logging method. And the MASW and SASW. MASW in the sense multi-channel analysis of the surface waves, and SASW is the spectral analysis of the surface waves. Okay, so for today's discussion, in the week 4 lectures, we have covered the seismic reflection survey, seismic refraction survey, and electrical resistivity survey. So we'll go into that method, and slowly in coming weeks we'll be seeing the magnetic anomaly method, gravity test, suspension logging methods, and all. So this, in the seismic reflection survey, what we see in the seismic reflection survey, first of all, for these seismic methods, we create some shock waves. Okay, seismic method, seismic reflection. So in the seismic methods, we create some shock waves. What are shock waves? Shock waves in the sense of disturbance. We create some disturbance. It can be like some impact loading, it can be some explosion, then some machine operation, traffic, and so on. Okay, this kind of disturbance we create to get the waves kind of structure. Okay, so we develop some kind of shock waves, and we develop this shock waves which travel as well as cause disturbance in the propagation of the medium. Okay, so we have several kind of seismic waves. Okay, we have the body waves, in which we have P waves and S waves. Then we have surface waves, in which we have the Love waves and Rayleigh waves and all. Okay, what are these waves, seismic waves? We'll understand from the presentation. Wait. Okay, so what we were discussing about the seismic waves. Okay, now these seismic waves that we are seeing, as I said, there are body waves and surface wave. Body waves means which happens in the body, you can say, or surface waves which are happening along the surface. First one was the P wave. P wave is also called as primary wave. In this, as you see, see, there is some shock at the origin point where you can see the XYZ coordinate. Okay, let me take the pointer out. Okay, see, so here what we are seeing, the waves or the disturbance is created at the origin, and how it is propagating. It is propagating in the longitudinal direction, and the particle motion is in this form, like it is traveling in this path. And let us consider one grid here. Okay, what is happening here? See, some compression happened, and again it has been came to the original position. So the direction of propagation in the P waves is like that, and see, compression happens and then it is coming back to the its original position. It will not happen that always it will come to original position, but to understand the P waves or the primary waves or the compression waves, whatever we say, we have to understand like this. Okay, so the particle motion is like in only the this side. Okay, next comes the S wave. S wave is also one kind of body wave. Now here what we are seeing, the at the origin, or wherever the disturbance or the shock waves is generating, it is traveling in vertical motions. See, so if you consider this part, okay, and if you see, it will start from here, and now when it is coming to this point, see, it is happening, the particle motion is happening in the vertical direction, and the direction for propagation is in the direction of waves. Okay, so it is happening in the body, and hence we call these waves as body waves. Okay, next one is the Rayleigh waves. In see, in the Rayleigh waves also, I am considering all the points I have created the origin as like this, and now again if you see it here, what happens, the waves are generated here, the disturbance, and what happens to the particle, see, the particle is moving some kind of circular like this, right? Again, let it come. See how is this particle behaving. See, the particle is behaving in some kind of path like this you are seeing. See, it will happen in this direction. Okay, and next one is the love waves. In love waves also, the particle, let us say this particle, how it is happening, the particle motion is in this direction, and the direction of propagation is in this direction. Okay, I hope you got what are the waves and why it is termed so. Okay, this S waves is also called shear waves. Okay, so these are some kind of seismic waves that is frequent, or that we see in like generally we see. Okay, so are you guys with me, like did you understand P wave, S wave, how the particle motion is traveling, what kind of motion is there for each of the particle in each of the waves? Anyone? Okay, understood. Okay, so we'll move to the next question. So the next question is, elliptical motion of the medium particles is caused by primary waves, shear waves, love waves, and Rayleigh waves. In the
Rayleigh waves.
Yeah, correct. See, the question is elliptical motion. As we have seen in these four waves, in the P wave, what is happening? The particle motion is in linear direction. Okay, so and the compression is happening, and the particle motion is in linear. Here also it is in vertical, but it is linear. In the Rayleigh waves, if you see, it's kind of elliptical, and in the love waves, it is happening in both linear direction. Okay, so the correct answer for the question will be Rayleigh waves. Okay, so let's move on to the next question. What is this? Which of the following wave is generated due to the heterogeneity in the soil deposit? Okay, coming to the heterogeneity, if we see, okay, let us, okay, switch off this. Okay, so now let us say that some kind of disturbance we are creating here, or let us say this is the source for the disturbance or the shock waves, whatever you say. So what will happen, it will create some kind of waves, right? Let me draw it like this. Let us say like this. Okay, so what all property, what all type of waves will be created, that will come later. But before that, what all we have seen, we have seen what are P waves, what are S waves, love waves, and Rayleigh waves. Now let us say if there are some heterogeneity in the sense we are considering the soil to be homogeneous. Okay, then only we are getting we are creating, giving these P waves, S waves, and all. But let us say there are some cavities, or let us say some other medium is there in the soil layer. So what will happen, some disturbance will happen, right? Let us say the waves are coming like this, it can get reflected, it can absorb, or some different kind of waves can generate. Okay, so now coming to the question. Mm, okay. So the question was, which of the following wave is generated due to the heterogeneity in the soil medium? Now, these waves are mostly generated because of the reflection that is happening from the heterogeneities present in the medium. As I said, as I mentioned, there was some heterogeneity like this. Let us say some local pockets which is available in the medium, which can be considered as the additional source of disturbance from which the waves are getting reflected. Anyway, let us say if we are having some second layer or some type of contrast, then the reflection will be happening like this. But let us say if we have some local pockets in the soil layer, what will happen? It will also cause some reflection, and that will be some other reflection, so which can be considered as some additional source of the disturbance from which the waves are getting reflected, or some energy is getting contained. So this will be recorded at the receiver at a later stage, like direct. Okay, that I have not mentioned. Okay, first we'll understand what are reflections and all, then we'll come back. Okay. Okay, so what we were seeing, what all things can happen. Let me rub this. Okay, now let us say there is some other soil layer present. Okay, this one is the soil layer 1. Let us say this one is the soil layer 2. So what all can happen? There are some receivers put, or receiver array of receivers that are put to get the seismic waves, what kind of seismic waves are generated, at what time it is reaching and all. Okay, so what can happen? Firstly, if we are creating some disturbance at the source, wait, so it can directly propagate through this, right? It can directly go here, and the receiver will get the signal as the direct wave. Okay, now what other thing can happen? The waves are generating, the black dots lines that you are seeing, the waves are generating. It will, let us say it is coming like this, it will reflect, it will get reflected back. Okay, like this, then again from here it is coming like this. So again after some time, some reflected waves will also be get caught in the receiver. Okay, so first one was the direct waves, then the reflected waves, then we also will see the refracted waves and all. So in the optics you might have studied the laws of reflection. What was the laws of reflection?
Angle of incidence is equal to angle of reflectance.
Reflection reflection Okay, so those are what all waves we have seen: direct waves, reflected waves, and what we said, let us say some heterogeneity or some local pockets is there. Again, from the source we are getting some waves. Okay, it will also create some reflection from here, also it will come, and it will have some reflection after some time to the receiver, so there will be creating some disturbance, right? So let us say, so waves which are, sorry, mostly generated because of reflection happening from the heterogeneities happening from the heterogeneity spelling heterogeneities, okay, correct, present the medium. Let us say like there are some local pockets like okay, that will create as additional source of disturbance, and these waves that will be created from this will be called as coda waves. Okay, so what happened? So the answer for this will be coda waves. You got yeah. Did you get the answer? Why? What is coda waves and how this coda wave is generated? Okay, so I'm considering you guys got what is coda waves. We'll move. So coming to the seismic reflection survey. Okay, before that I will explain what is reflection survey in small thing. Okay. So what I was explaining was seismic reflection survey. So what will happen? These waves will be created like this, and it will propagate through the medium, right? And the reflection will happen like this. And if you create the normal, this will be equal to this, the angle of incidence. So what will happen in the seismic reflection survey? Let us say the this receiver I'm naming as receiver A. So what will happen in the receiver will get some kind of waves. So the first that will get in very less time will be the direct wave. Okay, let us say the wave is like this, and again we are getting some waves, let us say. So this will be time and this will be the amplitude of the wave. Okay, so the first wave that we are getting from the source will be the direct wave, and after that, after some time, we'll get the reflected wave. See, this the graph that I'm showing is a very simpler form. The soil in the natural condition will not be this simple. Firstly, it will not this much homogeneous. It will be not linear. Again, we can have the linear contrast, or the soil layer that I have. Soil layer 2 and soil layer 1, the interface I am showing is horizontal. I am considering. If it is not horizontal, it is having some linear trend, then also there will be some other alternative for this. Okay, so what we are getting, we are getting the direct wave. So the time that we are getting for direct wave, let us say this one, we are considering that as TD, or the time at the direct wave, and this we are considering as TR, that the time at the reflection. So what is happening, how we are how we'll get the P waves. Now before that, how will we understand whether the source is P waves or S waves? it depends on what kind of source we are giving. Let us say we are giving the impact load. So what will happen if it is impact load, whether it will be P wave or S wave, what kind of waves it will be? Anyone? Let us say if we are having S wave, but if we are having vertical impact load, okay, then it will be kind of P waves. Okay, if we are giving vertical impact load, or let us say explosion, that will come under P waves. Or it is not like only P wave will be there, but other signals will also be there. S waves will also be there, some part of Rayleigh waves will also be there, but the dominant wave that will be generated because of the impact loading or the explosion will be the P waves. The S waves that you are saying, let us say we are doing some horizontal striking of rod, okay, resistance against some lateral movement, okay, which is resisted against the lateral movement, that will be S wave dominant. I'm not saying that P wave exactly means only P waves will be there. For impact load also, there will be some other waves that will be generated from that shock. But the dominant wave that will be there because of the impact loading or the explosion will be the P wave. So the impact vertical loading or the explosion will be P wave dominant. Got it? Okay. So and again one more question is there. Let us say if we are having stiff material, harder material, then what will happen? The velocity will be high, and as we go softer, or let us say it's not that harder, the velocity for the primary waves will be slow velocity. Okay. Okay, so how we are going to calculate? Let us say the P wave velocity in the first layer is Vp1, and in the second one it is Vp2. So how we are calculating Vp1? The Vp1 will be simply equals to, let us say the length between the source and the receiver is L, and the thickness of the soil layer is, let us say, capital H. Okay, so this one will be the incident wave, and this one will be the reflected waves. Okay, so Vp1 can be easily be written as L by Td, because see, in the reflection, if you go, we have one incident wave and the reflected wave. Okay, so there also we can calculate Vp1, the total length, the length of the incident wave and the length of the reflected wave total will do, and divided by the time that we have got, that Tr. Okay, from there also we can calculate the Vp1, but the thing is, for different soil layers we'll have different length for the incident wave and different this reflected wave. Okay, but we know the length between the source and the receiver, so easily we can calculate using the L and the direct time, or the time that is taken for the direct wave. Yeah. And as I said, how you are calculating the reflected waves time, that is Tr, let us say let us give some name, this name as A I have given now, let us say B, this is O. So time equals to distance by velocity. So what is the total distance? That will be BO plus OA divided by the velocity. See, the velocity we have got from this formula easily, Vp1 equals to L by Td. Now we have this Vp1, and BO plus OA we have to determine. Anyway, for reflection what will happen? Anyway, the angle of incidence is equal for the normal, then incident wave and the reflected wave will be equal. So we can write this as 2 of OA, let's say, divided by Vp1. Okay, now this, if you use simply the Pythagoras theorem, it will be written as root over L by 2 square plus h square. Okay, if I am doing some mistake, let me know. Okay, Vp1, okay, this one is the L, हम इसको extend करते हैं, this one will be L by 2 Don't go for my drawing, it is somewhat cartoon only. Okay, whatever. So 2 by this one, hence we can write this as tr equals to 2 will get inside, then L square plus 4h square by Vp1. So using that, if you want to determine what is the thickness of the layer, we can get it from here also, because anywhere tr we are calculating when it is reaching the receiver. So tr we have, Vp1 we have got from this formula, Vp1 equals to L by Td. So L we know, okay, so we can get the thickness of the soil layer easily, right? Now let's do some problem. अच्छा इसको stop करना होगा. Okay, so the question is, during a seismic reflection, sorry. During a seismic reflection survey of loose deposit of sand underlain by horizontal bedrock. Okay, so loose deposit of sand is there and it is underlain by horizontal bedrock. Okay, an impact is created at the source placed at 39 meter from the receiver. The arrival time of direct wave and the reflected waves are marked by the receiver as 42 milliseconds and 276 milliseconds respectively. Determine the thickness of the sand deposit. You guys take pen on paper, whatever. It's a simple like thing. You can do it easily. Do it. Do it. Let's say. Oh, what is the answer? Options I'll give. Let's see. Option A. Anyone else? Anyone else got the answer other than Srinath? Abhishek, Mr. Satish.
There is some error in my calculations. So,
Okay, okay. Mhm. Abhishek, any answer? Okay, let me do it. Let's see what is the answer I'm getting. Calculation mistake. Okay, let me do it. Mhm. Srinath, you have given two options. Which one you are saying? Option E or option A? Okay, let me do it.
Option A, sir.
Okay, let's see. Do it here. Okay, so what was the question? During a seismic reflection survey of a loose deposit of sand underlain by horizontal bedrock, an impact is created at the source placed at 39 meter from the receiver. So the length is 39 meter. The arrival time of direct and reflected waves are marked by the receiver as 42 milliseconds. So TD is 42 milliseconds, and TR is given as sorry. TR is given as 276 milliseconds. What is the question? Determine the thickness of the sand deposit. So just now we saw how we are getting the thickness of the sand deposit. We have that formula, right? TR is equals root over some 4h square L square plus 4h square divided by VP1. This one we got, right?
yes.
Okay. And how we are getting VP1? VP1 equals L by TD simply. Now L is how much? 39, and TD is 42 milliseconds. So 42 into 10 to the power minus 3 seconds. How much we are getting? Where's my calculator?
975.
975. Huh? Full pen check. How much did you say? 9?
975 meters per second.
975. I'm not getting.
928.57.
No, that is what I was getting. 928.571, something like that, meter per second. Check once. Okay, now TR is, just put the values. TR is given as how much? 276. Okay, how to remove this? Sure. 276 into 10 to the power minus 3.
Oh no, it is coming to 975 only. You have to divide it 39. Acha, okay, okay. Right, right.
39.42. I'm getting that only. 928.5714 something. Mm, L is 39 square plus 4 8 square divided by 928.571. Can you do this? Let's see how much is this. Okay, let me do it. 76 into 10 to the power minus 3. 76 into 10 plus 3 into 928.57 whole square minus 39 square divided by 4 root 16040. 16040.29. So I'm getting something like 126.65 meter. Any option like that? So it's like 0.126 kilometer. Correct is the option A. Everyone got? Maybe you guys have done mistake in
Yes, please.
calculation. That's it. Abhishek, did you get? So the correct answer will be A. Okay. Okay. So we'll move to the next question. Okay. So the next question is: a loose deposit of sand is underlain by bedrock during a seismic reflection survey. Again, the receiver marks the arrival time of direct and reflected waves as 50 meters second, 50 milliseconds and 300 milliseconds respectively. As a result of impact loading means what? P waves dominant. At 45 meter from the receiver, assume the soil profile as horizontal. The P wave velocity of the sand layer is. This is simple. We'll get.
900 meters per second.
900. Let's see. Other. Everyone got the same answer? It's simple only because TT is given as 50 millisecond. L is given as 45 meter. Sorry. Millisecond. Therefore, VP1 or VP equals simply L by TD. That is 45 by 50 into 10 to the power minus 3. Whatever will be you'll get will be the answer. 45 by 50. No, sir. It will be simply 900 only. 900 meter per second. Everyone got the answer?
Yes, sir.
Okay. Abhishek? Okay. Okay. This one was simple only. Okay. Next is during a seismic reflection survey of loose deposit of sand identified by okay, same question here, I guess. So the question is what it is the same question before and before that. Okay, what will be the velocity of shear waves and shear modulus of the medium if the Poisson's ratio is given as 0.27? Okay, Poisson's ratio, before moving into that, um, this P waves can be written as something like Vp. The S waves and P waves can be related like this: Vp by Vs is 2 into 1 minus nu divided by 1 minus 2 mu root. Okay, this one is the relation between the P waves, S waves, and nu is the Poisson's ratio. Okay, this P waves and Poisson's ratio is given. Now Poisson's ratio is given, you have to find out the velocity of shear waves. Velocity of shear waves means shear waves, as I said, is the nothing but the S wave. So you have to find Vs first. Now Vp you know how to calculate. Poisson's ratio you can easily calculate the S wave. Calculate, let's see what is the answer that you guys are getting. You just use this formula. Sorry. Use this formula, that's it. Options is given. Shinazi is getting option C. Anyone else? VP1, as we have calculated before, it was something like how much it was. VP was how much? Sorry. VP 928.571 meter per second.
That's right.
928.57 meter per second. What did you say?
Yes, yes, correct.
Option C you are saying.
VP, you told at
Ha
night
ha ha.
28.5. That's
Yeah.
correct.
Okay. Calculate the VS from the given formula.
Option C is coming to be correct. 521.23.
Okay, everyone is getting option C. Okay, let's see. I'm not doing that then. Anyway, my option is also C only, so it will come as 521.23 meter per second. Okay. Okay, so we'll move to the next question. And other than this, we can relate the VP and VS with the bulk modulus. Oh, okay, wait. The question is left. We have to find out the shear modulus also. I have not given the option for shear modulus. You have to calculate the shear modulus of the medium also. Okay, can you do that? Formula I will give. Okay, see, VP can be written as K plus 3/4 of G divided by rho to the power half or 1 by 2, and Vs can be written as root over G by rho, where K is the bulk modulus, G is shear modulus, and rho is the density of the medium whatever you are referring to. Okay, so for calculating the shear modulus, you need at least one of those. Okay, you need one parameter also. Let us say it is given as deposit of sand. Let us say the density of sand is given as 1600 and 1602 or something. Okay, let us consider at 1600 kg per centimeter cube. Okay, using this, can you guys calculate what is the shear modulus value?
It will be per centimeter cube. No?
Centimeter cube, I said, I didn't write. Sorry. Calculate the shear modulus. Simply use one of these, whatever is required, and get the value. Not sure what will be the answer. Let me see. Be cautious with the units. Okay, I have given the units in kg per centimeter cube, and the velocity that you have got for shear waves and p waves are in meter per second. Abhishek, can you say the units? Anyone got anything? 4.35 10 to the 14 kg meter per second square. So value I guess is correct because both of you are getting something like that. Mr. Shatish, can you check once or tell me
Oh
how?
no, no, I could not calculate.
Okay, simply use this formula. This Bs is equals to root g by rho. Rho we have 1600 kg per centimeter cube. Vs we have 521.23 meter per second. Okay, just use that and get the bulk modulus. Let me see how much we are getting. Square 521.23 square into kg per centimeter cube. Like to take a meter, take 6 milli. 10 power minus 3 sir. Into 1600 into minus 3 10 power minus 9 10 to the power minus 9. Sorry, 10 power 6 multiplied with 1600 into मीटर टेसी सेंटी 100 से डिवाइड होते हैं 10 पावर माइनस 2 10 पावर माइनस 6 10 पावर माइनस 6 271,680.713 into 1600 into 10 to the power minus 6 somewhere near to what is now why it's not g equals 434.69 kg per meter second square, something like this I'm getting. Okay, just change this to 1600 into 10 to the power 6, sorry minus 6, 10 to the power minus 6 से नीचे मल्टीप्लाई करो प्लस 6 kg per meter cube. And just do the calculation, you will get somewhere near to this. Did you get how to do that? Then we'll move to the next question then.
Yes, yes, yes.
Okay, everyone got right, and then we'll move to the next one. Okay, so we're moving. Next question is which of the following statement is or are correct regarding the electrical resistivity method? Okay, coming to the electrical resistive method, we do not have any question from पता नहीं, ठीक है जो भी है. So in electrical resistive method what we do, we have, let us say there are several, we have anodes here, we connect those by ammeter, then by some batteries, and then we get the current, and in between we keep one voltmeter to get the potential difference. Okay, so as we have seen in the seismic methods, seismic reflection or seismic refraction, shock waves will be generated, and the subsoil characterization is based on the resistance that will be offered by the medium against the seismic waves. Whatever waves, p waves, s waves, whatever waves is there, based on the resistance to that we'll get the medium. But in similar way, the resistance that will be offered by the subsoil medium against the electric current, if we do this, the electric current will flow, right? So the electric current will be flowing, so the current will be passing, and then using that, what how much resistance we are getting, using that we'll get, okay, let's say this type of equipotential lines we'll get. What is equipotential line again? Okay, this kind of equipotential line from both the side, okay, we'll get, and the flow lines or the current lines will also get. So how will the current flow? Current will flow from one electrode to another electrode, so it will be something like this. On the surface also, it one flow line will be there. So these are called flow lines or current lines, and these are the equipotential lines. Okay, now based on this, uh, based on the electrode spacing and how much resistivity we are getting, based on that we'll get the properties and the what type of soil type is there, that we'll get. Okay, so in the figure you can see there are some what kind of this structure or geometry is this equipotential line, and what kind of geometry is the flow or current line will be there in this question, I guess. Yeah, so the question is, which of the following statement is are correct regarding the electrical resistivity method? Option A is equipotential lines are confocal hyperbola, current lines are confocal hyperbola, current lines are confocal ellipse, equipotential lines are confocal ellipse, both A and C, both P and D, or all of the above.
Option E is correct, both A and C.
Option E. Anyone else? Srinath, Abhishek. Anyway, we can see in the figure that the equipotential line that we are seeing are kind of hyperbola, and the flow lines or the current lines that we are seeing are kind of ellipse. So those are the confocal ellipse. So the correct answer will be both A and C. Okay, so E will be the correct answer. Okay, so as I said, these are the potential electrode and these are the current. Okay, that I will write here. These are the potential electrodes and these two are the current electrodes. Okay, you guys have understood the method, then I will not go into the how the process is involved, or do I need to explain that? Okay, so we'll move. Okay, so the next question is, during the electrical resistivity survey or test, after a specific electrode spacing, resistivity was observed to increase. Okay, which of the following statement is correct for subsurface at the site? So you might have seen, like, there will be a plot between the electrical resistivity and the okay, so it would be electric spacing. How to rub this? Okay, so in the x-axis it will be electrode spacing, and the y-axis it will be the resistivity. Okay, now let us say this one is my threshold marks. So what will happen? Let us say if it is a homogeneous soil, then what will happen? The whole layer is a homogeneous soil. Then how will be the plot between the electrode spacing and the resistivity? If it is homogeneous soil, current is passing. Okay, then if it is the whole soil is homogeneous, what will happen? The resistivity for the whole layer or the whole layer which is homogeneous will be constant. So let us say if we have number 1 is homogeneous soil, then what will happen? The whole layer that we are considering is homogeneous, so the resistivity at every point will be same, so it will be something like this. Number 1. Let us say second one is the for the Let us know. Okay, let's say we have two layers like this. This is the ground surface. The first one is having low resistivity, and the other one is having high resistivity. Okay, I think here we have to not write. Okay, whatever. Then what will be the situation? What kind of plot it will be? In the top layer we have low resistivity, and in the bottom layer we have high resistivity. What will happen? So as the
With more of spacing, this lower layer also comes in picture. So resistivity will increase.
yeah,
With depth, more of resistivity will be
yeah,
there.
let's say if the electrode spacing is here, what will happen? The current will flow from here to here only, correct? So in electrical resistivity, what we see that if we increase the electrode spacing, what will happen? The current will flow for much greater depth. So if we are increasing the electrode spacing, the current will flow from for much deeper depths. So if we are here, let us say the two electrode spacing are here, and then what will happen? It will only go for some shallower depth. Now if we are increasing the electrode spacing, what will happen? The current line will flow much greater depth. If we are increasing again, it will go much greater depth. So what will happen after some electrode spacing? What will happen if we are going far than that? The current line will also follow this high resistivity. What I meant to say is, let me change the color. So here first, here and here the electrode spacing was there, then it will flow like this. If you increase the it will go like this. Again you have increased the electrode spacing. What will happen? The it will also go at deeper depths. Okay, yes, let me write this. Sorry. Okay, so it will go at deeper depths. So what will be the curve? As electrode spacing will increase, first of all, the for low resistivity it will be constant for some point, then as the high resistivity layer is coming, it will increase like this, correct? This will be the second one means low resistivity layer overlying the high resistivity layer. Okay, let me give some other condition. Now I will flip this. Okay, now the high resistivity will be on the first top layer, and the second layer will be the low resistivity. Then what will happen? Okay, high resistivity overlying low resistivity layer. Then what will happen?
This curve will stoop down.
So what will happen? First, when the high resistivity layer is the at the first layer, then what will happen? It will go constant, and after we are increasing the electrode spacing, it will go in the second layer also. As we are moving the electrode spacing, as I said, it will go at deeper depths. Now at deeper depths, what kind of resistivity is there? The second layer that we are saying is the low resistivity one. So what will happen? The resistivity will go down. So after some point, it will go down like this. Okay. Okay, next one. Now let us say we have high resistivity layer between two lower resistivity layer. Now, like for now, what I considered was the two layers only. One layer was having low resistivity or high resistivity, then some other layer. Again, let us say there are 3 layers, 4 layers. There can be so many layers if we go at greater depths, right? So what will happen? Let us say the fourth condition. Now one high resistivity layer is there between two low resistivity layers. Now what will happen? As the electrode spacing is moving, first we have the low resistivity and we are electrode spacing is at this point. So anyway our point will go like that. Okay, now we'll change the color so you'll understand. So what will happen at first, at the electrode spacing is increasing, it will only go through the first low layer. Okay, first low layer. So that time our resistivity will be somewhat constant. Now what happened, as we moved much, it will go to higher resistivity. So what will happen, the resistivity will increase. So after some time, let us say the resistivity increased. Okay, it is increasing. Now again if we are moving the electrode spacing far, yeah, kind of parabola curve only. So we can't say it as parabola because we don't know the resistivity value. Okay, it will be something like, first it will come constant, it will go higher, again if we are increasing the electrode spacing it will go much deeper depth, that is in the third layer what we have, the lower resistivity, again the layer will resistivity will come down. So something like this. We can't say it as perfect parabola, but it will be something like, it will come like this, it will increase and then it will decrease again. Okay, so this one is the fourth. Now one more situation, let us say several some discontinuity is there in between high resistivity layer. Okay, the layers are there, three layers, then we have some discontinuous in between. So what will happen, it will be some kind of, it will go like this and something like this, and it will come like this. So okay, so this one will be the fifth one. Okay, you got how electrospacing will affect the resistivity and all. Everyone, Srinath, Amika.
Yes, yes, yes.
Okay, so let's see the question. Okay, sorry. Okay, how to remove this? Can I select this? I what happened? Shit. Okay, I'll draw this again. Otherwise, it will be a problem for people. Give me 1 minute. Okay, I have to draw this because you guys have to see the recording. Resistivity, high resistivity, and this one is the ground surface. These are the electrodes. It will go like this, and this. Okay, now I can rub this. Okay, sorry. What is happening? Ah, okay, let me do it again. It's coming. So options are low resistivity layer underlying high resistivity layer. Okay, what was the question? I forgot. During the electrical resistivity test, after a specific electrode spacing, resistivity was observed to increase. Which of the following statement is correct for the subsurface of the site? Options are low resistivity layer underlying high resistivity layer underlying low resistivity layer, low resistivity layer overlying higher resistivity layer, and a soft layer is underlying a stiffer layer. Option A you are saying.
Option B.
Option B. Okay, anyone else? Read the options properly and then give the answer. Okay, so the question is, after a specific electrode spacing the resistivity was observed to increase. Okay, now read the options. Srinath, read all the options. Abhishek, read all the options.
B. High
B.
resistivity layer underlying lower resistivity layer.
Okay, anyone else? Anamika. Read all the options, everyone.
B and C.
C is also correct.
Yeah, That's why I said not read all the options. See, B and C are same only because it is written as higher resistivity layer underlying the lower resistivity layer, and in C it is like low resistivity layer overlying higher resistivity layer. Both are same only, right? So for that, the correct answer will be both B and C. Okay, B and C. Abhishek, you got it? Anamika? Okay, so the correct answer will be B and C. Shall I move?
Yes, please.
Okay. So next question is, at a site a limestone layer is sandwiched by a sand layer at the top and the metamorphic rock layer at the bottom. Okay, which of the following interpretations can be made while conducting the electrical resistivity test on site? So the options are like this. The options are very big. Resistivity increased with increased in electrospacing. Okay, let me draw it first. This is the sand layer, then is the limestone, and then is the metamorphic rock. Now it would be easier for you. What we are saying, which of the following interpretation can be made while conducting the electrical resistivity test on the site? Okay, resistivity increased with increase in electrode spacing. Okay, resistivity will increase कब कब अगर resistivity होता है, ठीक है. Resistivity decreased with increase in electrode spacing. Resistivity increased after a certain electrode spacing, then decreased. What is this? Then decreased, increased after a spacing. What is this?
A appears to be correct.
But read all the options also. And then decreased. Oh, ये ज़्यादा हो गया, ये डबल वर्ड लिखा गया, sorry. And the option C is like resistivity increase. Okay, this increased, I have made mistake, this twice it came. Resistivity increased after a certain electrode spacing, then decreased after a specific electrode spacing. Okay, and next is resistivity increased after a certain electrode spacing, then again increased after a specific electrode spacing, and none of the above. Okay,
D.
which one? D you said. Okay, Abhishek also
Yes,
said
please.
C. Srinath?
Sir, it's D.
Yeah, okay. So why A is not the case? Because in that it is saying that resistivity will increase with electrode spacing, but here we have three layers. Okay, so what will happen? It will increase, then again some other layer is coming, so again it will increase. So how will be the graph? Let us say it's electrode spacing. I am writing like this. This is the resistivity. What will happen? It will, after some time it will increase, then again it will increase like this. Correct? So the correct option would be option D. Okay, everyone got? Okay, we'll move to the next question then. Okay, seismic refraction test. Okay, should I need to explain the seismic refraction test, or you guys have seen? In the as seismic reflection survey only, what will happen in the other layer, there are, let us say there are two layers and there is one interface in between two. So what will happen, the layers will be coming like this. Okay, I'll draw. So let us say this is the source. What will happen? One direct wave will be there, then reflected wave will be there, which will get reflected like this. But some of that based on what kind of rock is there, whether it is coming to softer or the harder layer, it will refract from the incident ray. Okay, like that, like optics only it is there. So in this also we have the seismic refraction test. Now what is the question? Following data were recorded for seismic refraction test. and on a horizontal soil profile. Question, what is question? Teriki. हम्म, अच्छा तेरी क्वेश्चन ही पूरा नहीं है, ये कैसे हुआ? Okay, what is this meter? So okay, आ गया ये, सॉरी क्वेश्चन बाद में आ गया. अच्छा, okay, anyway, you have seen the option but we have to do that. Okay, maybe in animation I put. So question is, at what distance will the direct and refracted waves arrive simultaneously? We have seen in the graph for that the direct wave will be coming, and then after some time reflected wave will be coming, and again after some time what will happen, the refracted wave will be coming. Okay, this one is the direct wave, this one will be the reflected wave, and this one will be the refracted wave. Okay, now we are doing for direct and refracted waves. So now the question is, at what distance will the direct and refracted waves will arrive simultaneously? Okay, if you guys have done the refraction part, you can do this, or else we'll do. For this I think you need to do the plot, because uh, in the exam it will not be given like this. It will, they will give the at what distance or what the, so what we need to do, we have to do a plot. Okay, plot between what? Okay, you can do this in Excel or something, or
Time and distance.
yeah, correct. So in the x-axis this will be distance, it is given in meter here. Let us say we are also considering in meter, and in y it will be time. Here it is considered in milliseconds, so we are also considering in milliseconds. So what we'll do, we'll plot this data that is given here. So we'll plot this. So let us say this is 5, 10, 15. Okay, so what will happen, see, after some time I'll give you something like this. It will be something like this, or maybe it's coming like something like this, and then something like this. So what we have to do, you have to just do this and this point that you are seeing where the slope is changing, that point will be considered as the critical point. Okay, I have made two plots. Do you understand what is the difference between the two plots? Okay, I will use some different colors. अरे पीछे कैसे जाएगा? Okay, so let us say for this we got till this. Okay, and the second one we got like this. Now so for getting the critical point, what we'll do, we'll just extend this line. We'll extend this line. The point where we'll get the intersection of those two lines, we'll consider that as the critical point. Okay, and the distance, whatever distance will be there, that will be considered at the distance at which the direct wave and the refracted waves will arrive simultaneously. Okay, so let us say for the first case, the slope that we'll get will be 1 by v1. v1 means the layer, sorry, the velocity at the layer 1, and this one, the slope for this will be 1 by v2, where v2 is the velocity for the layer 2. Okay, so if we calculate, for this, if you plot the graph, and then you get what, at what distance both the lines are intersecting, you will get the answer. Okay, you got how to do that? If you got how to do that, we'll move, because it will take time to do in Excel, or you have to plot somewhere and then you will understand. If you got the concept, we'll move.
Yes, please. We can move. Simple.
Okay, okay. Abhishek, Srinath, Anamika got. Okay,
Yes, sir.
okay, so we'll move. So the correct answer for this will be A, 30 meter. You can note it down, note the question, you can do it later, or you can see the recording also. I'll upload the recording. Okay. Uh, sorry. Okay. Okay. Again, the next question. The same question is given. but the question is different. Okay, so the question is what will be the thickness of the soil layer. So for the thickness of the soil layer in seismic refraction survey, if you go through the derivations and all, you'll get the thickness as formula as h is equals to dc by 2 into root over v2 minus v1 by v2 plus v1. As I said, what is v1? V1 is the velocity in the layer 1, v2 is the velocity in the layer 2, dc we got in the last question. Dc is the distance for the critical velocity, or the distance at which the direct wave and the refracted wave will arrive simultaneously for the to the geophones or whatever receiver we are considering. So dc in the last question we have seen dc is 30 meter, right? 30 meter only, na? Yeah. Now calculate the thickness from this formula. Check how much you are getting. Okay, oh, v2 and v1 also you need, na? Okay, fine. So v2 and v1 how to get? You will get from those slopes from the plot. Okay, you can do it this in Excel and then you can get. I'm not sure how much v2 and v1 I have done this. Wait, let me check. Mm. You can do it once. v2 you'll get something like 416.67 meter per second. Sorry, this one will be v1, and v2 you'll get something as 1428.57 meter per second. Okay, if you put this in the this formula, you'll get, check once how much you are getting. v2 and v1 I gave. What will be the value for thickness? Anyway, you got the concept, so I think you can do it. It's simple. You have to plot that. The slope for the first one will be 1 by v1. From that you can calculate it v1. From the second line you will get the slope as 1 by v2. From there you will get v2. dc you got the distance at which both have the intersection, and just put in this formula you will get the answer. You will get at something like 11.11 meter b. Okay, so I'll move to the next question. I think this will be the last. Sorry. For better result, the spacing of current electrodes and the spacing between potential electrodes in case of Schlumberger array should be maintained as. Okay, the electrical resistivity that I was explaining, in that we have different kind of arrangements. Okay, and for every specific arrangements we have given it as name. Okay, and there are Schlumberger array, then Wenner array, and Lee array, and all. Okay, so in case of Schlumberger array, how was the configuration? It was something like, let us say this is the ground surface. We have current electrode here, we have current electrode here, we'll have ammeter, as I said, ammeter here, batteries, this is ammeter, and there will be, this is the potential electrode, as I said, right? So this potential electrode and all I say, and if you get the midway, this one is S or SP you say. Okay, spacing between the potential electrode. Okay, and let us say this one is A or SC. This one will be SP, SA. Then for this one will be Schlumberger array. For better results, the it will be something like 5 into A. Okay, so the correct option will be B, and from this we can calculate the resistivity also. For Schlumberger array it is something like pi A square V by AI. V is the value of potential difference, I is the current, A is the distance between the potential electrons, and SP will be that. or S you can say. Okay, similarly this one was Schlumberger array. We have Venner array also. Venner array, the same configuration will be there, just the distance will be equal only. Okay, so what will be the case? Some ammeter and battery, sorry, potential electrode will be like this V. So if you divide this, then all the values are, let us say, A only. So this configuration is called as Venner array. Okay, so for this question the correct option will be, which one will be the correct option? 2SC is greater than 5SP. Okay, that's it. Okay, that's it. Any questions other than this? Okay, kahan gaya? Srinath, you are asking about the question 9 and 10 of the assignment 3, na? If you are getting the solution by this week, then it's fine, or else I'll discuss in the next class if you want, if you are not getting the correct answer. Okay, I didn't
There is
check
some
the
issue with question number 9.
Oh, is there, na? Srinath was
Oh,
also
yes,
saying
yes.
that there was some issue with the question 9. He is
Yes,
getting
yes.
some other option
I
as the
tried, I tried number of times. It's not coming.
then it might be possible that there are some error in that. Okay, anyway, I will also do. Let me see how much I am getting. Okay. Okay. Any other query? Any other question? If not, we'll
Well presented.
wrap it up. Thank you.
Thank you, sir.
Okay. Thank you. Okay. So next Monday we'll meet again for the week 5 discussion session. Same time, same link. Okay. Thank you so much. You guys can leave. We'll stop the recording. Thank you, Anamika.